This rock is dangerous. It is uranium ore, contains a large amount of uranium oxide, and is therefore, obviously, radioactive. It's a shame that humans can only measure radioactivity using detectors, but can't see it. Or can we? This is a cloud chamber, and it allows us to do exactly that. If you don't place anything inside, it makes the ever-present background radiation, such as cosmic rays, visible. But I will place this small radioactive rock inside the chamber. Next, an alcohol such as ethanol, methanol, or in my case isopropanol is added onto this felt inside the chamber. As you can see, the chamber also has a metal grid under the felt. You will see what that's for in just a moment. Once I have sealed the chamber with a glass dome, I turn it on. What happens now is that the plate on which the radioactive sample lies is cooled down, and after a short time you can see vapor trails in the chamber caused by the ionizing radiation. The short, thick trails are caused by alpha particles, and the long, thin trails by beta particles. A high voltage can be applied to the metal grid I just mentioned, which helps make the vapor trails more visible. But how does a cloud chamber work? The principle is surprisingly simple. The alcohol I poured onto the felt evaporates and saturates the air inside the chamber. Near the cold bottom plate, the alcohol vapor cools down and becomes less soluble in the air. It becomes supersaturated. It wants to condense into a mist, but needs a small nudge. And that nudge comes from the particles generated by radioactive decay. The alpha and beta particles provide the missing energy needed to overcome the metastable state and form vapor trails. The basic principle of a cloud chamber is thus very simple. I built the small chamber in one of my first YouTube videos. Theoretically, you can build a cloud chamber using a drinking glass, a metal plate, and a bit of dry ice. But as you can see, my large rock doesn't fit in the small chamber, so I decided to build the largest DIY cloud chamber ever made. While building the small cloud chamber was relatively simple, building a large cloud chamber that can run continuously is much more difficult. Some of you may have already noticed that the small chamber can't run indefinitely. Eventually, all the alcohol evaporates from the felt and condenses on the cold bottom plate. At this point, the chamber stops working and you have to remove the alcohol from the plate and put it back onto the felt. This means that this process has to happen automatically in a continuous cloud chamber. And that's just one of many problems to solve. So, let's get started. Everything begins with a 4mm thick 35 by 50 cm brass plate. This is the plate that later has to be cooled down to -30°C. But how do you cool down such a large plate? In my small chamber I use so-called Peltier elements. These are thermoelectric heat pumps and are ideal for building a small chamber. If a voltage is applied, one side of the Peltier cooler gets cold and the other one gets hot. But unfortunately, they are absolutely unsuitable for cooling such a large plate. One of the Peltier elements in my small chamber consumes 8 amps at 12 volts. Even if I wanted to cover only 1/3 of the plate's surface with Peltier coolers, that would still be 33 coolers. If I connect them in parallel, that would require 260 amps. In series, that would be 400 volts. If connected in series, the failure of one element would mean the chamber stops working and could possibly damage all other elements. For this reason, large cloud chambers are usually cooled with a compressor, just like a freezer. This is not only much more efficient and uses less energy, but is also much easier to maintain. In a refrigeration cycle, the refrigerant is compressed and liquefied, releasing heat through a radiator and fan. It then flows through an expansion valve or capillary tube where the sudden pressure drop causes it to evaporate and cool down. In the evaporator, the cold refrigerant then absorbs heat from its surroundings. This means that in the case of the cloud chamber, I have to turn the brass plate into the evaporator. To do this, I use a copper tube that I bent into a shape that covers the entire surface of the cooling plate. Or at least I try my best. Bending a copper tube flat and covering a surface evenly is harder than it sounds. But in the end, I had a passable result. Next, I needed to connect this copper tube to the brass plate in a way that conducts heat very well and is permanent. This means I have to solder the tube to the plate. The problem is I want to avoid soldering the tube piece by piece to the plate because I'm worried that uneven heating could warp the plate. So, how do you heat a large metal plate to about 250 degrees Celsius? Exactly, with a camping stove. After sanding and thoroughly cleaning the plate and the copper tube, I placed them on the camping stove and heated them. Since the copper tube doesn't lie perfectly flat on the brass plate, I used a generous amount of solder, about 500 grams, and bonded the tube to the plate as well as possible. Before the solder hardened, I placed weights on the copper tube to press it against the brass plate. If you enjoy projects like this one, consider subscribing to my channel or supporting me on Patreon. You will find the link in the video description. A huge thank you to all my current Patreons for their generous support. After removing the flux and cleaning the plate, the result wasn't pretty, but the tube was firmly attached to the plate. And more importantly, the plate was still perfectly flat. Now I just need a compressor and my cooling cycle is complete. Since I don't know much about refrigeration systems myself, I'm glad that a viewer named Alexander offered not only a compressor, but also his help with the initial assembly. He is a tinkerer himself with a little tinkering paradise. That's exactly what I love about this community. One of the most valuable things I've gained through my YouTube channel is the exchange with other people. First, we installed a high pressure switch that shuts off the compressor if the pressure on the high pressure side reaches a problematic level. Not exploding is a nice feature to have. We also installed a filter dryer that removes moisture from the refrigerant. As it turned out later, this would become very relevant. The pipe connections that need to be disconnected later were equipped with flare fittings. This allows me to replace key components such as the filter dryer, the expansion valve or the evaporator. In an initial test using propane as a refrigerant, the plate reached a temperature below -30 degrees Celsius, even without insulation. That's definitely good enough. A huge thank you to Alexander for his help and the compressor. Back home, it was time to build a frame that would house the compressor and onto which the brass plate could later be mounted. For this, I used aluminum extrusions. They look sleek and are modular, so I can make adjustments or add components later if needed. In general, T-slot aluminum extrusions are the coolest stuff ever. If I had 3 wishes, one of them would definitely be an unlimited supply of aluminum extrusions and connectors. In the lower part of the frame, I installed a plywood board where I could mount the compressor. To do this, I screwed threaded inserts into the board so I could later bolt down the compressor. Before mounting the wood board to the frame, I gave it a coat of varnish. Then the compressor was mounted onto the board with multiple bolts. So now the question is how to attach the cooling plate to the aluminum frame. I designed a part in Fusion in which I can mount the brass plate and that fits onto the aluminum frame. The problem is it's about 5 times larger than the print bed of my 3D printer. So my 3D printer worked overtime and printed the frame in 8 parts. I could then glue these parts together. I have to say, 3D printing is probably the most revolutionary technology for tinkerers. It's just amazing what a 3D printer makes possible. Many of the holes you see are for threaded inserts. In general, I use threaded inserts wherever possible, so everything could be easily assembled and disassembled. With 3D printed L brackets, I could then press the plate against the 3D printed frame. And in a first test, the printed frame fit remarkably well. To make the vapor trails clearly visible, the surface of the plate must be well lit. For this, I installed a very bright LED strip that cost a good $120 for 5 meters into a 3D printed holder. Unfortunately, this solution wasn't very satisfying. As you can see, the lighting casts shadows on both sides of the plate, and the light emits at a too wide of an angle, meaning you get blinded when looking into the chamber from the side. So I scrapped this attempt. Next, I bought a light bar, like the ones mounted on trucks, since the light should be both very bright and very focused. But this was also a bit of a flop. In this case, the light was too focused, which meant that not the entire plate was illuminated and the rest was unevenly lit. In a third attempt, I printed a new holder for the LED strip. Since the chamber is huge, most components are too large to print in one piece. So these LED holders were also printed in 3 parts. At this point, I want to give a huge thank you to Bamboo Lab. The X1 Carbon from Bamboo Lab printed over 5 kilograms of PLA for this project without a single failed print. Yes, Bamboo Lab provided me with this printer for free, but I have no obligation to mention it in this video. There's also no affiliate link. I'm simply very satisfied with this printer. Now that everything is glued together, you can finally see how the new lighting solution works. The lights can be tilted to adjust which part of the plate is illuminated. At the same time, the top cover ensures that you are not blinded by the light. There are still some small shadows visible on the edge, but I don't think I will be able to get rid of them completely. And the main area of the plate is very well lit. By the way, the lights you are seeing right now are a prototype. The final ones won't have the glue residue on the outside, and the posts holding them will be nicely rounded. To power the lights, compressor and other electronics that will be needed, I installed an electronics box on the wooden panel. One switch is for the compressor and the other one for a 24-volt power supply that will later power the rest of the electronics. Some of you may have noticed that I also installed a potentiometer. With this, I can control the speed of the compressor fan via a phase angle controller. This has the advantage that the cloud chamber isn't quite as loud, and it also allows me to control the temperature of the refrigerant on the high pressure side. If the refrigerant gets too cold, it might collect in the high pressure loop and not reach the cooling plate. In the meantime, a very important package arrived with an essential part of the cloud chamber: the glass cover. While I used a bell jar for my small cloud chamber, the large one will have a rectangular flat cover. For this I had an aquarium custom made. I chose special white glass as it doesn't have the classic green tint of regular glass and gives the best view to the inside. Okay, let's see if the glass dome fits or if I measured something wrong. Oh, perfect. Nice. As you can see, the glass cover has an extra hole in the side. This hole can be used to change the sample while the chamber is running or to inject a radioactive gas. I think it's time to talk about an obvious problem. How do I generate the alcohol vapor inside the chamber? In my small chamber, I used felt that covered the top of the chamber. That's not possible in the large chamber, as I want to be able to look into it from above. So I need to come up with a different way to introduce the alcohol into the chamber. For that, I bought aluminum U-profiles and drilled a small hole on each side. The holes hold small plastic parts that allow me to connect a hose. I also closed off the ends of the U-profiles with 3D printed caps. The plan is to pump alcohol into one side through the small hole so that the channel fills with the alcohol. Since I need to ensure there's always alcohol in the channel, I either have to carefully control how much I pump to avoid overflow, or take the easy way and let the alcohol flow out the second hole on the other side. So I continuously pump the alcohol in a loop, avoiding the hassle of monitoring the fill level of the channel. I then mounted these channels on pillars inside the chamber. To pump the alcohol into these profiles, I use a peristaltic pump, which I also mounted on the wood panel. And do you remember when I said the alcohol condensed on the cooling plate must also be removed? If not, the plate would eventually overflow and you would constantly need to refill the chamber. That's exactly what I designed these channels in the 3D printed frame for. They allow the alcohol that collects on the plate to drain off. A second peristaltic pump removes the alcohol and collects it in a reservoir. This way, the alcohol is always pumped in a cycle and never lost. The first peristaltic pump moves the alcohol from the reservoir to the U-profiles where it evaporates. The evaporated alcohol condenses on the cold plate and is pumped back into the reservoir by the second pump. At least that's the theory. To control the peristaltic pumps and also to read the temperature of the system at various points, I designed an additional controller box. This box contains 2 Arduinos that can read multiple temperature sensors and allows the speed of the peristaltic pump to be adjusted via 2 rotary encoders. So I would say it is time to test the recirculation system. Okay, the cloud chamber is now level, so I can use some IPA and squirt it on the top surface here to see if the drainage system successfully removes it and collects it in this beaker at the bottom here. As you can see, the problem is that it is leaking at the bottom. I really hoped that the basically interference fit between the cold plate and the 3D printed part would be enough to stop IPA from seeping through there, but it looks like I have to add some kind of sealant. After sealing the plate with silicone, I tested the system again. It seems to work. As you can see, there is a thin layer of IPA on the cold plate. The IPA is draining through the drain ports I've shown you earlier, flowing through these plastic tubes here, through the peristaltic pump and into this collection beaker. There is some IPA leaking, but that is just on the side of these connections right here. I didn't want to glue them in permanently. On that occasion, I also reprinted the parts needed for the lighting, and of course, I managed to drill myself into the hand in the process. I just drilled myself in the palm. I noticed that this extrusion here doesn't reach far enough into the opening here on the top. And I just thought I would drill it out, and while holding the part like this, the drill actually punched through the part I wanted to drill at the top here, and I drilled myself in the palm. Be right back. After I had taken care of my wound, it was time to fill the cooling circuit and test the entire system for the first time. For that, I first need to cut all the copper pipes to the correct length and then resolder the flared connectors I've mentioned earlier. Oh, as I was about to fill the system with refrigerant for the first time, a package from today's video sponsor arrived. PCBWay offers not only PCB manufacturing, but also 3D printing and milling services for a wide range of materials. Whether it's aluminum, titanium, stainless steel or various plastics, you simply upload a 3D model of the required part to their website and immediately get a price estimation. I had a new frame for the cooling plate made by PCBWay. The 3D printed part worked great, but a piece milled from a solid block just looks better. I chose PUM as the material for the frame because it's both rigid and resistant to solvents like isopropanol. So if you also don't have the means to manufacture certain parts yourself, check out PCB's website. You will find a link in the video description. A huge thank you to PCBWay for being a long-time sponsor of this channel. Unfortunately, milling has one small disadvantage. Unlike 3D printing, internal structures cannot be milled. This meant I couldn't have the small channels milled through which the isopropanol can drain from the plate. Therefore, I used 3D printed brackets to drill holes in the correct positions and then opened the channel completely with a rotary tool. After also adding threaded inserts into this frame, it was time to install the cooling plate. The only problem was that I now had to remove the old cooling plate from the 3D printed frame. As it turned out, this wasn't easy due to the silicone, but after about half an hour with a screwdriver and a hot air gun, I was finally able to free the plate. I figured that since I already had taken the plate out of the frame, I should use the opportunity to make the surface black. For my small cloud chamber, I had used vinyl foil for this, so I thought I would do the same for the large chamber. But as it turns out, it's nearly impossible to apply this foil perfectly without at least some very small imperfections on the surface. Even a small crease from shipping will show in the final result. So I decided to paint the plate with a matte black 2-component lacquer. The first attempt went, let's say, moderately well, as I accidentally got my finger too close to the nozzle, causing 2 large paint drops to land on the plate. So I had to remove everything and start over. My deepest respect goes out to the people who managed to perfectly wrap or paint a car. It looks easier than it is. The second try went much better and I ended up with a nice matte black surface. Next, the brass plate was mounted to the new frame and a temperature sensor was attached to the underside of the plate using epoxy resin. This way I can later read the temperature of the cooling plate on the controller box I previously built. I then insulated the underside of the plate with foam. This should help achieve a lower temperature and prevent ice formation on the bottom. Now the new assembly could finally be screwed to the aluminum frame. I then also mounted the aluminum channels through which the alcohol will later flow onto 3D printed pillars. I also added heating wire with a silicone coating into these channels. I can use these later to warm the alcohol, which will result in faster evaporation. Otherwise, the alcohol will slowly be cooled by the inside of the chamber and the evaporation rate will be too slow to produce nice vapor trails. Where were we again before the package with the new frame arrived? Oh right, I wanted to test the refrigeration system. So let's finally do that. As a refrigerant, I'm again using propane from a simple camping gas cylinder. As it turns out, that was a mistake. Although the refrigerant R290 is simply propane, the propane in camping gas cylinders contains significantly more moisture, which would later cause problems. Before filling the cooling circuit, I evacuated it with a vacuum pump for several hours to remove residual moisture and then left it under vacuum to ensure there were no leaks. Filling it with propane went smoothly, but the moment the expansion valve, the place where the refrigerant evaporates and gets cold, reached sub-zero temperatures, the cooling stopped working. The reason was moisture in the propane, which then froze at the small nozzle of the expansion valve, blocking it. By continuously heating the expansion valve, I was able to keep the cooling circuit running, and over time, the moisture was absorbed by the filter dryer. Within half an hour, the plate reached a temperature of -40 degrees Celsius. A complete success. The pumps also worked, reliably pumping the alcohol into the channels and removing it again from the plate. And with a small piece of uranium ore in the chamber, you could already see the first vapor trails. But there are several problems. On the one hand, the alcohol does not evaporate fast enough, but I already have a solution for that. On the other hand, the top of the glass cover gets so cold that moisture condenses on it and obstructs visibility. I still need to figure out what to do about that. Another problem is that my solution for the high voltage doesn't work well. My goal in building this cloud chamber was to make it look as sleek and elegant as possible. At least the upper part, meaning the actual chamber. That's why I wanted to avoid an additional wire for the high voltage in the chamber. I thought I could simply apply the voltage to the aluminum channels that contain the alcohol and serve myself an extra component in the chamber. Unfortunately, that didn't work. On one hand, the alcohol does interesting things when a high voltage is applied, but more importantly, the adrenos in the controller didn't like it when several thousand volts were applied, even though technically they were insulated from the high voltage. So let's solve all of these problems so that the cloud chamber finally works as it should, and I can show you what happens when a radioactive gas is injected into the chamber. To make the alcohol evaporate faster, I cut felt mats into appropriate sized pieces and mounted them in the channels so they could soak up the alcohol. Thanks to the large surface area, the alcohol should now evaporate much faster. And since I had to disassemble the channels anyway, I solved the high voltage problem at the same time. I printed new posts for the channels through which I can run a high voltage cable. At the top of the post, the cable comes out again and can be connected to a thin brass tube. This way I have separated the high voltage from the alcohol and all other components, and I think it still looks very elegant. Wait a minute, I just realized that I never showed you where the high voltage comes from. I find it incredibly difficult to make structured videos about projects that span several months. Anyway, this is a flyback transformer, like the one used in old CRT monitors. The circuit board it's mounted on allows the output voltage to be adjusted via a potentiometer. I also mounted this transformer onto the wooden board, and the controller box allows me to switch the high voltage on and off. With that settled, I wanted to clean up the mess that is the current wiring. So I did some cable management and neatly routed the hoses. And when I moved the capillary tube that leads to the expansion valve sensing bulb, I suddenly heard a hissing sound. As it turns out, the capillary tubes in old expansion valves are made of copper and are quite sensitive to repeated bending. A break in this tube cannot be repaired, meaning I had to buy a new expansion valve and replace the old one. And that in turn meant I had to release all of the propane. So I connected a small Bunsen burner to the cooling circuit and safely burned off the propane. When the new expansion valve arrived, I installed it and took the opportunity to use proper R290 refrigerant to avoid the expansion valve freezing again. Once that was done, I finished routing all the cables and hoses. The whole thing looks much better now. I'm thinking about installing side panels on the aluminum frame to hide the compressor and electronics a bit. Let me know what you think about that idea. The last thing I need to address is the glass fogging up. I considered using those thin heating wires found in rear car windows. However, you would always see those wires on the glass, and I would have to design a connector, probably with pogo pins, that makes contact as soon as I lower the glass box. Professional large cloud chambers solve this problem by having a second, even larger glass box over the inner one. Warm air is passed through the gap between the two boxes to prevent condensation entirely. That's certainly the most elegant solution, but not feasible with my design. Maybe in a next iteration. My solution is an infrared lamp mounted on a gooseneck. Now I just need to screw in the actual IR bulb and... Believe it or not, but this is the second time that happened to me. So I ordered a third socket and tried again. I would say it's finally time to test the cloud chamber in its finished state. I'm not really happy with the way the vapor trails look. They are wide and don't really look nice. My guess is that the electric field created by the high voltage isn't uniform enough, since the electrodes are only placed on two sides of the cooling plate. I tried solving this problem by stretching 3 very thin, barely visible wires across the inside of the chamber. The result looks much better, but is still far from perfect. Nevertheless, I'm very happy with the result. Fine-tuning a cloud chamber is an art in itself. I will definitely continue working on optimizing the balance between evaporated and condensed alcohol to improve these vapor trails. My next step would be to design a channel that not only surrounds the cooling plate on two sides, but completely encircles it. Hopefully, this leads to a faster and more uniform evaporation. I promised you that I would inject a radioactive gas into the chamber. So, let's do it. This syringe contains radon. To collect the radon in the syringe, I simply stored a few small pieces of uranium ore in it for a week. In the decay chain of uranium, radon is also produced, which accumulates in the syringe as a gas. Through the hole of the glass cover, I can now inject this gas into the chamber. You can see how the radioactive radon spreads throughout the chamber and completely fills it with vapor trails. Radon is an alpha emitter, which is clearly visible from the short and thick vapor trails in the chamber. I have been called an art philistine by my friends before. I find it hard to understand how people can stand in front of a painting for a long time, fascinated or deeply moved by it. But for me, a cloud chamber is a beautiful example of the fusion of science and art. I suppose the feeling I get when I look into the interior of a cloud chamber is the same feeling others have when they look at a painting like the Mona Lisa. I really hope you enjoyed today's video. Other than that, thank you a lot for watching.